Okay, so enough third year volunteers are there in the room.
Hello.
Vedant, tell me.
Yes, sir. Just starting. So, should we start, sir? Or waiting?
Yeah, 1 minute, Vedant. I'm audible, right?
Yes, sir.
Yeah, okay. Right. So, good morning to all, the participants, right, on the second day of the workshop. Okay, right. I hope the yesterday's session proved helpful to you, right? And I think even the lab sessions in the afternoon, right? That is what I got to hear from speakers, right, and the student volunteers. Right? They felt it was we were able to proceed with the initial starting exercises or whatever you put them in Python. Okay, right? So continuing forward, right? So today's session, right? The first speaker will actually cover or give an exhaustive, you know, session or discussion on the power of Python for data representation, visualization, and pre-processing techniques. In fact, the way we have structured it, the yesterday's afternoon sessions, right? They are more of a general purpose exposure to Python, right? So I think from today, possibly you will see the speakers actually tapping the power of Python for in fact the pre-processing setup, right? I think that forms the one of the first set of phases, right? And just to introduce the speaker, right, Vedant Basi, right? But for me, I refer him as Vedant, right? He is an applied AI engineer at Signay Technologies, right? And he is a dual degree pass out MTech computer science, right, or MTech computer engineering, right, from our institute, right, and a student of or a past student of my courses, right, and I think I'm not reading out from any slide, right? These are my own past students, right? So I take the liberty of recalling it from my mind, right? So regarding Vedant, right, I recall him as one of the best students with an implementation repertoire, right? I think right from the second year when he was a student of our institute, right, I could see that flair of the implementation repertoire in him and his what excellent ability to translate the concepts or whatever we have in mind, right, to put it into practice, right. He was one of the go-tos for me, right, and I surely rate him very high in terms of the ML capabilities, right. I think now at least we differentiate between AI, ML, and all, right. I think he will be a real repository when it comes to data science skill set, right, and the other techniques which I exposed you yesterday, right, and the great strength of him, right, when it comes to correlating in Python, right, the way I think he possibly will always opt for the optimal package or optimal way out for a given solution or for a given requirement on hand. Okay, right. Santosh, you can start recording. Okay. So I think I could not have possibly had, I think, as I said yesterday, right? Each of the speakers whom we have allotted some concept in data science or pre-processing, right? They possibly are the best bet as far as I am concerned, right? I may be biased as their teachers, right? But I think that is what the feedback also I got to hear from his industry hirees, right, or hirers, right? They were quite happy with this what repertoire, right? All that stuff, right? So without delaying too much, right? I think the room is having around 35 people, right? But they presume people will keep joining in, and not to hold the others who are on time, and also not to drag the speaker, right? They're all in a work from home syntax. So I am quite confident, right? This session, right? You possibly may not have a dedicated lab, but I think that is the way Vedant would have planned, right? So as he presents concepts, their corresponding Python code will also be put across and be shared to you on a Jupyter or Colab online setup, right? So that you can run them and see, feel the output, right? So I think the second session will be in my mind, right, where I touch upon association rules, right? But I think my request to you people, right, because you don't have the lab session for this, pre-processing forms one of the key steps, right? That's what I told you yesterday, right? Forget mining, forget data science. Data analytics by itself can answer much of the requirements from a real-time point of view, right? So this is one of the how do you clean the data, how do you avoid unnecessary data, right? All that stuff he will present on, right? So pay the required importance to this session, right? And I should thank Vedant for taking his time out from his industry schedule, right? So I now request or hand over the session to Vedant.
Thank you, sir, for that amazing introduction. Couldn't ask for more. Good morning, everyone. Welcome to the second day, session 1 of the ATAL workshop on data science with Python. And today, as sir said, we are going to introduce data representation, visualization, and pre-processing techniques. So let's just dive right into it. Let's start with why we need to visualize data. So assume you have a very large data set. The first thing that you need to know is that just by scrolling through a data set, by that I mean, let's say you have a very large CSV file, comma separated values, or you have a very large number of images, or you have a very large number of basically any huge data set. To understand the data, you would not start going through it number by number or word by word. What you would do essentially is you would convert it into a visual representations, or you would extract certain key attributes from that data set that help you understand very clearly what this data means and how it is going to help you and what are the complex patterns in this data set. So what we technically can call this as is to understand the distribution of the data. And we need to understand how different attributes in the data set interact with each other. And before generally in machine learning or in AI, before we apply any algorithm, there are multiple ML algorithms that are available for our use cases. Before we apply any algorithm, we need to be very clear about what our data looks like and what it represents. So to get that intuition before applying a machine learning algorithm, we need to understand the data. That process is called EDA, exploratory data analysis. That's a separate field which is built on top of visualization entirely. It is extremely helpful in taking data-driven decisions. So what that means is if you have generally seen that people take large, for example, business decisions, and if a business decision is driven by data, then in most cases, to make their point, they visualize all the data that they have using these tools. And those are called data-driven decisions. Checking the quality of the data is extremely important. In a lot of cases, we have noisy data, we have missing values, or we have certain spikes or outliers. So checking all of this stuff through these techniques is very easy. Coming to the last point, when you have purely numbers representing your data set, then you can extract very easily statistical measures like mean, standard deviation, median, all these measures. But even after you have a look at these numbers individually, as they say, pictures speak 1,000 words. So you will get a much clearer representation when you actually finally visualize the data. So I'm going to start off by explaining the basic libraries that we will use during this session. So it all boils down to three main libraries. We have pandas, numpy, and matplotlib. So I believe in yesterday's session you might have been introduced with these libraries and some basic calling functionality and what they do, the power of these libraries might have been displayed. Today we might go a level deeper, especially into matplotlib, because this is the main library that we will use to visualize the data. Later on into the session, we will explore pandas and some very specific functionality of pandas for pre-processing our data. And numpy is the numerical Python library, which we will use for as the basis for storing our data and for all kinds of basic data operations like addition, subtraction, or concatenation of arrays and such operations. So these three libraries are available for Python, and additionally, I have this link here, which I will copy and paste into the chat. You can check it out. This is basically where I refer for more. I would refer you to for more such libraries in other languages. And if you want more graphics, you want more features, you can check this out. So moving on to the next slide. Let's start with the basic numerical statistical measures on the basis of which we can start building our visualization methods. So I'm just going to discuss three very basic ones, which are mean, median, and IQR, quartile range. So starting with mean, it's very simple. Arithmetic mean essentially means that it's the sum of the values divided by the number of values. So let's say you have a data sequence x1, x2, xn. So x bar generally represents the mean, and it is represented as x1 plus x2 up till xn divided by n. So two properties of the mean that I would like you to remember always is that it is very susceptible to outliers in the data set. And what that means is if you have very extreme values or if you have very skewed data distribution, then I would not recommend that you go for the mean. And number two is that the mean need not be in your data distribution. So these two values are extremely important. So in case you need your output to be not susceptible to outliers, or if you want your output to be part of the distribution, then do not use the mean measure. These are the two key values that I'd like you to remember though. So the mean can be computed using numpy. So NP here stands for numpy, and this is the short form. So when we import numpy as NP, that's the code line that we give, and np.mean, this is the simple command that we can calculate the mean with for this sequence of arrays, this array basically. So this is the mean, and next we'll check out median. Median can be described as the middle number when you sort a sequence of numbers, and if let's say there are even number of if the range of numbers is even, then it is half of the lower middle number and the upper middle number. So that can be represented using this formula. If there are odd number of numbers in the sequence, then it's exactly the middle number. So median, the best property of the median is that it is not susceptible. It is not susceptible to outliers, whereas mean is susceptible to outliers. So what that means is, if let's say you have very extreme values, then even then median is extremely good at representing or ignoring those values, because ultimately it only depends on the exact center of the distribution when you sort the numbers. So this is median, and we can actually modify median calls such that if you want exactly a number from the same distribution, then you can always stick to the lower middle or the upper middle. So those minor modifications can be made, but ultimately medians are not at all susceptible to extreme values in the data. And coming to interquartile range, So this is the last statistical measure that we'll discuss. So interquartile range is very simply put, it's the difference between the 75th percentile and the 25th percentile. So what this means is you have a sequence of numbers, in this case, right from 63 to 81. If we split based on the middle number, which is the median, uh, this is a sorted sequence. So if we split based on the middle number, which is 72, take the lower half, take the median of the lower half, and if you take the upper half and you take the median of the upper half. Now, the difference between the median of the lower half and the upper half is the interquartile range. So I hope that's very clear. It's the difference between the 75th percentile, which is the median of the upper half, and the 25th percentile, which is the median of the lower half. So that is a very simple explanation of IQR, which is the interquartile range. So now with these three measures in mind, I think we can proceed with our first visualization technique, which is the box and whisker plot. So this is a very easy to visualize and very easy to understand plot, I would say. But it has a lot of hidden features that might not be apparent to if you don't know what it means. So this is what the box whisker plot looks like. Box whisker plot is very convenient in displaying different distributions side by side and checking the spread of the distributions. So one thing to note is box whisker plot. So okay, so the middle line here, as you can see, marked as median. If you have a sequence of numbers, the sequence of numbers is now represented using this box and its two upper and lower whiskers. So that's why it's called a box whisker plot. And the middle line here is marked. So all this, just for your information, all of these markings, everything will be done by the libraries that I'm going to show you. You just have to provide the sequence of numbers that you would like to plot. So yeah, continuing, that generally there's a middle line which represents the median. There's a lower quartile, which is the lower end of the box. There's an upper quartile, which is the upper end of the box. Now, I have described IQR in the previous slide. So this distance between the upper quartile and the lower quartile is called the interquartile range. So the upper quartile and the lower quartile. So this upper quartile is the 75th percentile. This lower one is the 25th percentile. And the whisker generally represents all the numbers that are between the lower quartile and the lower extreme. So this lower extreme has a very specific formula, which is Q. Well, it's not relevant in our use case, but here's one thing to remember: anything beyond this lower extreme and anything beyond this upper extreme is considered as an outlier, which will be plotted as a single point. For every outlier, you will see a single point. So this is what the outlier is. So box whisker plots, because of this reason, give us a lot of information about number of outliers. They will give us information about the middle 50% spread, which is the IQR. They give us information about the median. Additionally, you can also get the information about the mean also if you require. And it overall gives the spread of the data. So this is very useful when data is symmetrical, or if the data is skewed in any direction, you can find out very easily. You can easily check outliers, as I mentioned already. And coming to the use cases, I would say the most appropriate use case for a box whisker plot is when you have multiple data sequences that you want to compare side by side on the same scale, and you would like to identify different kinds of skews or different kinds of spreads in the data that generally occur in your data set. So for example, if you have data coming in from multiple duplicate machines and you would of the same product, and you would like to visualize all the data side by side. So here's a small example of that. So you have company A, B, and C, and the number of stocks sold on the x-axis. So here, as you can very clearly see, company A has, the lower quartile has more values as compared to the upper quartile. The median is shifted towards the upper. So the upper whisker has a much longer range. So what this means is that the number of values that are present, or rather not the number of values, the actual number of stocks sold in the upper whisker are higher, number of stocks sold in the lower whisker are lower, and the spread of the data is actually, I would say, medium compared to company B and C. Company B has a much wider spread of the IQR. Company C has a much smaller spread of the IQR. So 50% of the values are contained within the IQR. So, and the rest 50% are either outliers or in the whiskers. So if you say that a company has a very small IQR, that means majority of the values are in this 4,000 to 5,700 around range. So here you can clearly visualize, okay, so clearly number of stocks sold is better for company C because they've sold more stocks, or whatever logic you want to extract out of this, but basically it's for comparison purposes. So coming to the code for whatever be your use case, here's a very general code, and I'm going to also copy the code and paste it on the chat again. So coming to the code, it's very simple. Here are your imports, which are NumPy and Matplotlib. These are the only two libraries that you will require. In this specific example, I have created a lot of random data, which we can directly analyze. So even if you don't have your own data set, you can very easily draw a box plot with this data, right? So here are the 5 data arrays that we are going to visualize. So there's spread, which is 50 entities. So again, there is this call called numpy.rand. So using this, you can tell NumPy that you want 50, an array of length 50 with random numbers between 0 and 1. We multiply those numbers by 100 for easier visualization purposes. And similarly, we take center, we take flyer high, flyer low, which is your whiskers, upper whisker, lower whisker, and your actual data, which is a concatenation of all of these arrays. So all of these 4 arrays. So finally, so this is just a small technique where we create random data for our very specific use case. It is not relevant as such to the box whisker plot, but we will see similar code snippets in the coming slides. So I'm just explaining it to you. Now, this is the most important line where we actually plot the data of the box plot. Now, if you just check out the URL, which I have posted in the chat, you can see this exact code, and you can copy it, paste it on your terminal, and you can in your Python terminal, and you can run it, or you can save it as a file and run it, and you will see a box plot occur, which actually represents this exact data. So so yeah, this one line, which represents the box plot calling function, this is all of it. And you don't have to actually calculate the IQR, the median, all of it will be automatically calculated. So that's the benefit of using Matplotlib. So that was box whisker plot for us. Next, we're going to see the bar chart. So a bar chart is generally used to show numerical comparisons across discrete labels or discrete values. So what this means is, let's say you have on the y-axis here category A and B, and on the x-axis you generally have a value that you would want to represent. So this is a bar chart. Generally, you do not have a continuous value or a continuous interval on the y-axis. Instead, you have labels. Essentially, one of the axes has to be labels, the other axis has to be the values. So histograms, on the other hand, we will see in the next slide, but histograms represent continuous values on one side and or on both axes, and they do not have any categorical variables. So okay, coming to bar charts, we have a lot of different use cases. Almost majority of our plottings in real life, I would say, can be covered with bar charts or stacked bar charts, and there are so many variants. But the most basic form, in the most basic form, bar charts are extremely helpful and used a lot in daily life. So they can be used for classifying nominal or ordinal categories. So what this means is, nominal means when our categories don't have any specific ordering, and ordinal means the opposite of that, which is that our categories actually have a very specific ordering. As an example of nominal, I would give the states in India, for example, Tamil Nadu, Karnataka, Maharashtra, etc. So there's no such ordering of the states. They are just states, and the basic kind of ordering that you can do is alphabetical, but as such, there is no ordering. Whereas when you actually look at categories like grades, which is your A, B, C, D, E, so there is an ordering where A is the highest grade, B is the second, and C is the third. And so you have an ordering in those categories. So generally, bar graphs can be used to represent both these orderings. And here is an example from the New York Times. They generally use a lot of visualization techniques to put out the news. And this is a basic example from them. So what's showing here is different companies and the taxes that they paid in federal taxes that they paid in 2018. And overall here, this is an example of a stacked bar chart because you have two stacks. You have the profit and the federal tax rebate. So this is known as the label here, or the legend actually. And these are essentially what you'll see are categories, or rather discrete categories, which you have not created. You have not set these intervals. These are just naturally occurring categories, right? Amazon is a separate company, and then Delta Airlines is a separate company. So this is what I mean by a bar chart. Whereas in a histogram, we'll see that in this case, this is a continuous interval, and we have manually divided the timeline into discrete bins, as they call it. So coming back to the bar chart, I'll show you the code for generating a bar chart, a very simple bar chart. So again, we have matplotlib imports here. Again, I'll copy the link and I'll paste it here for you. So so yeah, we import both the libraries, matplotlib and Python. These are the only two libraries that we'll be using throughout for visualization. We have, in this specific example, what we're doing is we're putting labels like adventure, action, drama. So these are labels for movies, and no number of movies is an array which contains the number of movies for each label. So this is a very simple example of the kind of data that bar charts can easily represent. And this is a function that I've created for plotting the bar chart. It's not necessary, but you can very easily create a small function for plotting the bar chart. But essentially, the line that you're looking for is plt.bar. So this is a simple line for plotting the entire bar chart, where index represents the 1, 2, 3, 4 variable numbers, which can be generated using this numpy.arange function. So again, if you just copy this entire function, your work will be much more easier, because in a bar chart you also have to plot the x label, y label, and the x ticks. These are the most important things. So what the x ticks represent are essentially the label name, which is adventure, action, drama, etc. So x ticks, as an example of x ticks, is this Amazon, Delta Airlines, Chevron, General Motors. So what you would have to do is this line is very important to plot the actual names of the movies. So this is an example, a very simple, like 20-line example for plotting a bar chart. And you can check the chat for a demo page for the bar chart using matplotlib. Now coming to histograms. So histograms, as I mentioned, the difference between bar chart and histogram is only that in histograms, we manually section the timeline into bins. So we say that from year 2000 to 2005, create one bin, and everything that falls in this category, put it in that bin. Whereas in a bar chart, the bins are not created by us. The data as such already comes in categories. This is a very important distinction. It's a minor distinction, I would say, but then it's a very important distinction, and especially when you're trying to code, and when you have the raw data at hand, you need to make that distinction as to what can be considered as a bar chart plotting and what can be considered as a histogram plotting case. So so as I mentioned, in histograms, the x-axis contains a continuous value, and the y-axis can also contain a continuous value. So histograms, we need to manually come up with these bins, or these basically buckets, you could call it, where we say that this is the length of the bucket. Everything that falls within this length of this bucket, place it into this particular column. So that we will represent using code, and that I'll show you in a second. So again, histograms are generally for a continuous variable, and even it is even better if the continuous variable has some specific ordering. That will be very helpful. So let's take this example, average number of press briefings per month by year. So again, I've picked up this example from the New York Times. They had come up with this representation. So what you can see is they have created these individual bar charts where they have created this histogram where they have created individual bins. Each bin, as you can see, represents a section of the year. Now, it is not 1 year. Instead, it is an arbitrary portion which they have predefined. So what that means is from 1997 to 2001, they have defined around 1, 2, 3, 4 bins. So that is up to their decision. So it is not naturally occurring. It is not a naturally occurring category. So I hope that's clear. And then they have additionally provided a divider for Clinton, Bush, and Obama and Trump administrations. And as you can see, very clearly, it is apparent in this bar graph, histogram, that the number of press briefings per year has dropped constantly. And this is like a very good implementation, I would say, of the histogram. And it gives a lot of information about where the trend is heading, or who, across the time period, who has taken how many press briefings. So it's a really good example. Now, coming to the code, again, it's a very simple function call. It's a single function call. So we have our imports. In the imports, we have two more lines this time, which is just to add color to the plot, and the other is a percentage formatter, which is it's nothing complicated. It's a very simple thing actually. So again, we take 100,000 points this time. We take 20 bins. So this is something which is new here, because we predefine the number of bins in our categories in our situation, because the X and the Y data that we have is continuous data. So we need to predefine that we need 20 bins, and the algorithm, all we will do is tell them that matplotlib .hist x-axis, this is the data which is stored in this x variable, which is coming from the numpy rand n function, and similarly you have y, which is based off of the x function. This is a random equation that we've created. It's not something that is it's just a way to represent or come up with random data. So we have x. In your case, the x and y can be anything that your data set corresponds to. So the x and the y, and for each we provide the n bins that we want to break the data into. And then finally we hit plt.show, which shows the actual graph to you. I'll copy this code and paste it on the chat again, so you can check out the demo for histograms. So again, all of these codes are directly executable, and they don't require any other libraries. If you have matplotlib and numpy installed, that is it, and you can directly get your hands dirty with histograms, bar charts, etc. So coming to violin plots. Violin plots are basically an extension or a better version, you could say, of box whisker plots, because they give a little more data about the data set, or the distribution of the data set that we are dealing with. So the inner part of this distribution is basically a box whisker plot, which we have seen in our first example. And this is again the IQR. The big dot is the median. Now, again, generally there is a dot or a line, whatever it is, but in Matplotlib, it is represented as a big dot. The straight line is our whisker. And finally, this entire purple region, or pink/purple region that you see, that is the distribution or the frequency of occurrence of that particular entity. So let's say here 0.1 is the entity that we are referring to. 0.1 might have been has occurred like relatively on the higher side compared to, for example, the value that is coming over here. So what this means is that this data is multimodal, and what that means is that there might be multiple modes of the data set. So as you can see, there are two spikes in this distribution. And by the way, this is the left and the right side represent the same value, so same distribution. So it's just a mirror image. And this is actually useful for actually visualizing the different modes of the data or the frequently occurring values of the data. Now, it can be used as like an improvement over the bar chart, or it can be used if you want to know if you know that you have multimodal data. But within this, all the data that is contained can be also visualized using a box whisker plot. Now, coming to a very simple example for the violin plot. And again, you can compare multiple distributions using violin plots, just like you can do it with box whisker plots as well. And you can very clearly check that your distributions are bimodal, multimodal, or just have a single mode. And you can visualize that very clearly here. Coming to a sort of a good example, I would say, is this image that I have found, where on the left and the right, generally in a violin plot, it is symmetrical, where it says whatever distribution is on the left is also on the right. But in this case, we can see that on the left, it says the population of males, and on the right, it says the population of females. And the gray area corresponds to the same data in 1997, and the red/maroon, I think, line corresponds to the same data, or the supposed to be the same features, but in 2017. So here, what you can see very clearly is how there is more of a skew in the population of females versus the population of males, and how the skew has increased over time, as in the red line extends further in 2017 compared to the gray line, which extends a little less in 1997. So this is a very good example of how they have used kind of like a violin plot. It's not exactly a violin plot, but kind of like a violin plot to represent so much data inside. I mean, this is data that corresponds to, so the y-axis is the age, and the x-axis is the population. And we have represented the age distribution from 0 to 100 in a single image, and it is multimodal data clearly because there are multiple spikes in the data. And it very nicely represents our understanding of the distribution of age and over time, and distribution of gender over time. So coming to the code implementation, again, it's all just a single function call, which you don't have to know how it implements internally, but all you have to know is how to format your data beforehand. So as in all the cases here, we have a very simple distribution here, or a method to create the random data. In these three lines, we are creating our random data. So we say that this is the POS, which basically is which we will iterate over in this line. So this is a little advanced way to represent our Python or create our Python data. But what it means here is we iterate over this array 1, 2, 4, 5, 7, 8, and we create random normal distributions with mean 0 and standard deviation as 1, 2, 4, 5, 7, and 8. And finally, we just concatenate all that data into a single array. So essentially, when you implement this, and again, I'm posting the link to the code in the chat. When you when you do run this example, what will happen is that you will see multiple normal distribution or a single normal distribution occurring with a constant fixed mean of 0 and different standard deviations. So a standard deviation of 1, for example, 2, 4, 5, 8, and you can see that as a violin plot. So you can actually see the frequency, and with the violin plot, it is highly configurable. As you can see, the number of points that you would like to plot, the width of the entire distribution that you want. So it's a configurable parameter. If you want to show the mean, if you want to show the extreme values, which is the outliers, you want to show the median. So I've set all of it to true in this example. But overall, you can configure each of these fine-grained features of the plot as well. And actually, in Matplotlib, there are so many other parameters that you can configure that, I mean, we cannot go into those in this slide, but there's a lot more things. If you read the documentation, you can find them out. So this is a very basic example of the violin plot. Moving on to the next, we have a scatter plot. So in a scatter plot, what happens is, as you can see on your screen, we have just the points scattered on a graph. That's it. So on top of the points, we may or may not plot a line of best fit, but ultimately a scatter plot is just points on a graph which are scattered according to the data that is given as the input. There is no mean, median, or there is no interquartile range that is specifically calculated on a scatter plot. And what scatter plots do help us understand is, if you do not know anything about the data, if you just have two continuous value distributions, your x and your y, then you can and there is a correlation between them, then it is very easy to plot a simple scatter plot and understand what is the relation between them, or what kind of attributes they are, or what kind of outliers are there in the data. So as an example, you might have data that has different kinds of correlation between the x and the y axis. There might be, for example, what we call as a positive correlation, negative correlation, or just no relation at all. And there might be a linear growth, there might be an exponential growth, or a U-shaped growth. There are so many examples possible, but here are just a few examples that I'm giving. This is not an exhaustive list, but this is just the way to understand that, okay, in my scatter plot, this is the kind of distribution that I'm seeing. And again, so there's something known as correlation strength, which in this case is very strong. It's a little weak here, and here it's basically there's no correlation. So again, so when you don't know these relations between your data, it's very easy to plot it using scatter and find out if there is any correlation, and or if there are any outliers, or if there is any apparent clustering in the data that you can do. So this is a very easy to understand plot. Now coming to a small example for scatter plot. For scatter plot, this example that I've given is basically 3 clusters that I've generated using these equations. So this equation is again using numpy.rand, and what we do is we use some parameters like 0.6, 0.4 here, and we generate random data, x and y coordinates of random data. So G1, G2, and G3 are 3 clusters that I've generated using these equations. So since we use the random function, everything in that cluster will have a certain type of will lie close to each other according to the x and y coordinates. So we take our data and we just put it in a so this bracket notation in Python is called a tuple. So G1, G2, and G3, and we create a tuple out of the data. And other benefit of matplotlib is you can very clearly specify the colors that you want for each of the data clusters that you have. And groups here represents the labels that you need to give for G1, G2, and G3. These are just arbitrary labels. They don't actually mean anything. So in this case, just as an example, I've given coffee, tea, and water. But ultimately, what you will do is you will iterate over this data, and you will call the scatter function with x, y, which is your coordinate details, and your alpha as a parameter that you can configure. So by default, you can, even if you leave it as empty, it is not, it causes no harm. But if you want to, for example, specify color very clearly, as we have mentioned here, so our colors will be red, green, and blue. And G1 will have red color, G2 will have green, and G3 will have blue color. And we don't have any edge colors. We have s equals 30. So again, this is a, I think it's a size parameter. I'm not exactly sure. And then finally, we have the label. So label is very important because when we specify the red color, at the top, we will get something known as a legend, which specifies that red color means coffee, green color means tea, and blue color means water. So that label is what we are providing here. So, and finally, we just give the plot a title, and we specify the legend exists and the location of the legend. So finally, we do plt.show, and that shows us the entire plot. Now, the only line that you have to remember is this one, which ultimately you will be using to plot your scatter plot. Everything else is just data generation in this example. And in your specific scenario, it will be whatever data you have as the X and the Y coordinate. Now, so I hope that is clear. And if there are any questions, you can please post in the chat. But overall, I hope that is clear. Yeah. So coming to the next visualization technique. I hope I'm not going too fast, but I think there's a lot of stuff to cover, so I might be going a little faster than I should be maybe, but please let me know if I am. So the line graph here is a very, I would say, as an example, the bar chart is to histogram as the scatter plot is to the line graph. So if you, just to explain that, what it means is, if you have a scatter plot, in which one of the intervals can be ordered in a specific direction, then if we connect all the points of that scatter plot in that specific direction, so that will give us a line graph. So what this means is, let's say that our x-axis here represents time. Now time is a continuous valued variable, and it has a very specific ordering. So by that I mean, like, for example, there is 8 a.m., 9 a.m., 10 a.m., 11 a.m. So 8, 9, 10, 11 comes one after each other, and there is a very specific ordering, right? So we would connect the lines from 8 to 9, 9 to 10, and 10 to 11, and so on. And this line would represent like the flow, or it can represent anything in your scenario, but essentially it's a scatter plot which has a continuous value distribution with a specific ordering, and it is connected by a line. So a kind of a good example for the use case of a line graph is this example from the New York Times again. So to give you an example of what the raw data behind this line plot must have looked like is, here, as you can see, the y-axis is the altitude and the x-axis is time. So what this refers to is actually data from a plane crash that occurred in 2018, 29th October 2018. And this is data from the sensors of that aeroplane that had crashed in Indonesia, I believe. So what had happened is that we have very discrete values at each second almost of our time period, which is from, in this case, 8:30 to 8:45, I think, approximately. And for each second that we have sensor values. So one thing I would like you to note is that we can very easily plot this using a scatter plot as well. We can very easily plot this using a bar graph as well, or even a histogram. But it is not uh, uh, as good as if we plot it with a line graph. So let's take the line graph example here. And very clearly seen here is the way. So I'll just give you a little background story to what happened during this crash. So there was essentially a sensor that controls your nose angle of your aeroplane automatically. And this was a new addition that was added in the Boeing 737 Max aeroplane. And this sensor automatically calculates the nose angle that is supposed to be there for the aircraft. Now, the pilot can also manually control the nose angle, but this sensor is an additional advantage, you can say. Now, in this very specific scenario, this sensor malfunctioned and is trying to bring the nose of the aeroplane towards the downward direction, whereas the pilots have taken off and are trying to keep the nose at the upward direction. Now, what's very apparent here is that there is a constant struggle between what the pilots are trying to do and what the sensor is trying to do. The sensor is trying to pull it down, and the pilots are trying to push it back up. And the sensors are trying to pull it down, and the pilots trying to push it back up. And this constantly happens for a period of approximately 15 minutes or 10 minutes after takeoff. And at the very end, as you can very clearly see, the sensor takes full control and it completely pushes it into a nose down direction. And finally, the plane crashes. So this is very apparent in this line chart. And additionally, it adds so much more detail when you actually, when they have provided these arrow to represent what's exactly going on. So this is a good example of a line chart. Additionally, actually, I would
Vedant?
Hello. I hope the screen is visible now. Santosh
Yeah,
sir,
it's
can you?
visible.
Yeah. Okay. Fine. Sir. So could you just tell me where I dropped off from? Was it the screen?
Yeah, this one.
Okay, okay, fine, sir. So basically, just moving quickly. So this is a very basic example of a good and a better sort of implementation where the line chart should be used appropriately and a histogram should be used appropriately. We shouldn't try to correlate both of them where it's not necessary. Just a design choice. But overall, let's move to the source code for our line graph. So source code of line graph is probably extremely simple. It is simply this one single line which contains your x and your y coordinate. So the x and the y coordinate, again, I'll copy and paste the code on the chat, or rather the link to the code on the chat. And yeah, and coming to the source code, we have matplotlib, we had numpy, and we have arange, which is a function that gives us uh, a range of numbers or an array of numbers within the range 0 to 2.0, and the difference between each number is 0.01. So this is a very simple function for getting an array. And then so basically this line chart, if you plot it, if you plot this line chart, what you'll get is a sine curve, because that is the equation that I've used to get this prepare the data. Basically, in your scenario, your specific scenario, you would just have to give the x and the y coordinate, and it'll automatically plot the data for you. And this is the final call which plots the data, plt.show. Additionally, if you want, you can give the x label, you can give the y label, which is your x and the y coordinate, and you can also give the title for the plot. Now, moving on to the next type of chart, a pie chart. This is a very simple chart, and just a note, this is best used when your data has ratios or proportions of something. I'm sure you're aware of that. I'm sure you've seen this chart a lot of times. And especially one place I would not recommend to use this pie chart is when the ratios of certain entities are very small, and so small that they are almost negligible. In that case, the pie chart, the slice will not be visible, and it is not useful in that scenario. But every time there is a ratio or a proportion of something, pie charts are a great way to show that visualization. uh, Now, coming to pie chart, the code example, let's take our labels. Let's say we have these 4 labels, and we say that the size of each label is represented using this, which is the number of entities. So they are not asking for the percentages; they're just asking for the number of entities. So number of entities of each type. And finally, if you want, you can give an explode parameter, which will sort of give a little bit bigger size to the second entity or the second class, which is HOGS, hogs, and it will not give a bigger size to the other entities. Very simple. And dot PIE, this is the function call for our pie chart. Again, we just pass our sizes, our explode parameter, labels that we have already come up with, and this is the percentage formatting function. It is, again, it is optional, or generally you don't have to give it. If you want, you can. And also you can give a start, you can customize it a lot. You can give it a shadow, you can give it a start angle, and start angle is basically where your first ratio starts from. So if you want, you can start from 90, or you can even start from 0 or 180. And finally, we just give so access dot equal is ensures that the aspect ratio, as I mentioned here, the aspect ratio of the pie chart is constant, so is equal. So if it's not equal, it might turn into an ellipse or some skewed representation, because that's one of the features of matplotlib, where we can actually very clearly specify the size, and if we specify the axis as equal, it keeps the aspect ratio as constant. So plt.show is the final call, which we use everywhere to show the plot.
One thing that I would additionally like to mention is if you like to save the figure as a file, like a JPEG or a PNG file, this is the command fig.savefig and test and the name of the file. So this figure will be saved in your same folder from which you are running the Python code from. And this command, you can keep a note of that if you want to save the file as a separate image. So coming to, so this was the code for pie charts. I think we're clear on that. And coming to density plots now. Density plots are, I would say, very rarely used, but they represent a little better understanding of data when it is very dense, when it is very essential to understand the distribution of the data in a from the top down perspective, or when you have a slice of a certain 3D data. So it's a little bit of an advanced plot, I would say, but overall it internally does smoothing of the data wherever necessary, and it uses certain kernel smoothing methods and to remove out the noise for parts of the data which you either don't have or which are outliers. So to create this exact example for a density plot, here is the code. So in this exact example, we create an X and a Y data, a data spread, which we usually do as in our examples. And finally, what we do is we have this plt dot p color mesh. This is the function call for a density plot. And additionally, if you want to, let's say, change the color distribution, I've also shown another call, which is the CMap parameter. So generally, if it is a density plot, generally people prefer to have very specific color values for high density regions and low density regions. So they do provide an opportunity to change the color. So in this P color mesh, what we do is we have Xi, Yi, and Zi. So these are the three variables. So X and Y represent your X and Y coordinate, and the Z variable represents the density or whatever value you want to represent in the third dimension, or as the color dimension, I would say. So in this case, it is each color point here matters a lot, because with the color we correlate to whatever value it is at that X and Y coordinate. So this is the function call for a simple density plot. If you would, I mean, density plots have very specific use cases. Generally, they're applied in cases where you have a 3D data, but you would like to represent it as a simple 2D image maybe, or you would just like to check a cross section of that data in a 2D format. Even that you can check. So so these are like basic, almost all of the basic plots that you can have in matplotlib. There are many more. They are more complex use cases, like as we'll see in the next slide. So here is a very sort of different use case where you have to combine multiple ways of representing data into a single plot. So what's happening here is you have a scatter, a box, a bar. You don't exactly have a density, but then using the scatter, a scatter plot can be used as a sort of density measure to show you number of plots. So this is the sort of mixed example, and generally in real life scenarios, we do go for these kind of implementations because generally real life data is more complicated, has a lot of correlations, has a lot of meaning attached to it. So we can create something like this using matplotlib, but that is not something I'm going to cover in this specific slide. But we essentially, I'm going to leave that for you to discover, but it is possible. Now coming to sunburst diagrams, this is again, we are just going a little bit on the extreme here. Sunburst diagrams are something that look like this, where we have multiple pie charts, and each concentric pie chart represents a subsection of the inner pie chart. So what's happening here is the node, uh, the yellow node and the orange node here, the yellow node has a certain proportion, and the outer leaf node has a certain sub proportion of the yellow node. So this is very well used, I would say, in the Ubuntu operating system. So in the Ubuntu operating system, we have folders, and folders have subfolders. And to represent the size of each subfolder as a proportion of the total memory, in Ubuntu, they use these sunburst diagrams basically. So again, so I'm just giving examples here of different ways you can stack different basic visualization techniques to make more complicated techniques. This is a very simple example that I found online for how sunburst diagrams were used many years ago, even before like visualization techniques were happening using code. But a small example here. So this is public schools and their educational institutions and the funding they have, and where each of the funding went and how it was distributed further. So moving on to the next, we have 3D surface plots. This is also possible using matplotlib. And 3D surface plots are, again, it's a corner scenario. It's a less frequently occurring scenario, maybe because it is difficult to collect this kind of data. But it is possible using matplotlib. And here is a small code example which I'm going to give. For this, I have pasted the code in chat again. Now, in a 3D surface plot, it is very similar to the density plot, where all you have to give is the x, y, and the z coordinates and the color map for those coordinates. And you have additional features like line width and anti-alias. So anti-alias is a bit of an advanced feature which is represents the interpolation between different data points. If you would like that to happen, you can enable it. And ultimately what you need to do is come up with this x, y, and z arrays which contain data which contain the data columns basically. In this specific example, if you would like to generate this very exact 3D surface plot, this is the code that you can use, and I've also posted the link in the chat. And yeah, I think we can move on because this is sort of a less used example, but I just wanted to cover it with a simple code explanation. So moving on to the next. So those were all of the, I would say, data visualization techniques that we can use and how to implement them using code, Matplotlib and Python. But before any of that happens, I there is another part where you have to pre-process the data, or you have to understand the exact granularity of the data, the format of the data types. And this is the section that deals with all that implementation detail. So generally, data can be segmented into two categories, categorical and continuous. So an example of continuous data is anything which has a continuous distribution. Basically, what it means is height, weight, price. These are values which are not discrete. Weight can be in your decimal places. Height can also be in decimal places. So can price, and so can profit. So these are examples of continuous data. And we have examples of categorical data, which are gender or grades. So gender is a categorical data. Grades is a categorical data. For example, it's like A, B, C, D, E. So each of these is a category. There's no further sub distribution after A. There's no decimal places after A. So these are examples of continuous and categorical data. So every time you have categorical data in your data set, it is difficult for algorithms to understand categorical data because they don't understand what coffee, tea, or water, or A, B, C, D means. It needs to be converted into a numerical format so that the algorithms that we use for visualization or for whatever machine learning algorithms that we use, those can understand that, okay, so the grades can be represented as a in the numerical format, and what it means, and so that we can apply some computation on that value. So we'll touch upon that in the coming slides, how to convert categorical data into numerical formats and different libraries to do it. And continuous data as such is already in numerical format, so that is very easy for us to directly ingest into our algorithms or visualization techniques that we use. So moving on to just a little bit of touch up on Pandas library. Till now, the examples that we saw were based on NumPy and were based on Matplotlib. But if you were to give NumPy a lot more focus on data handling per se, then you would get the Pandas library. So Pandas library is very specifically used when you have large amounts of data that you want to process, lot of pre-processing techniques built in. So just a small example before we move on to the benefits of Pandas. This is a simple example of how you can read a CSV file. CSV stands for comma separated values. Generally, all of our data is stored in CSV files, which basically means that it's a table of data which has multiple columns and multiple rows. So with this single line, pd dot read CSV, read underscore CSV, we can read the entire CSV file, and most of your entities will be automatically inferred by the Pandas library. You don't have to give any further values unless your CSV file is very complicated and has very additional features. If it's a normal CSV file, it will automatically infer all of the fields that are required, including the table, including the column names, if there are any, including the data type, including the separators that is used in your CSV file. So here are a few benefits of Pandas. I think I already mentioned a few. Infers data types, extremely fast for reading data sets because it has a very specific focus, which is it is built for that scenario. And it has large number of built-in tools for cleaning and processing the data. We will see in the coming slides how we can use that. It's easy to add and remove columns. So generally, we have a lot of inter-column interactions between the data. So we can very clearly and very easily do that in Pandas. So we can also add more columns, remove columns, drop columns, all that. And it automatically infers headers and footers in CSV file, which generally do occur in a lot of cases. And generally, in a lot of our datasets, we have timestamps, we have dates, and all of these things, Pandas directly infers them, converts timestamps into different formats for you. It will convert dates into different formats for you. And all of this is additional features which NumPy does not have. You can read CSVs using NumPy, but Pandas is generally preferred because of all these extra features that it comes up with. So, and obviously there is error handling, which we will address in the coming slides. So in Pandas, or rather in data pre-processing, there are multiple ways to pre-process the data. Now, generally, when you have a very large data set, it is natural and expected that we will have some data that might be missing, some data which might be wrong, it might be noise, it might be anything that is wrong with the data that needs to be fixed before we pass it into an algorithm that does machine learning or data science, whatever it is. We have to ensure that our data is as pure as possible from our side. So that needs to be done using data pre-processing. And these are decisions that generally you will take before you pre-process the data. So you need to understand, maybe using visualization techniques, or maybe by going through the code base, you can going through the data set, you can understand what kind of missing data you have and whether you'd like to replace that missing data either by filling in the missing values, you can ignore the values, or you can basically remove. So this is for missing data. But let's say you have noisy data, for example, and a good example of noisy data is when your age variable is negative. So age cannot be negative. So that is, but what if it is in your data set? So how do you solve that problem? So you can solve that using multiple methods. You can either ignore it, but let's take the scenario where it's not age, it is something that has a specific ordering and can be inferred from the column above it and the row above it and the row below it. So in that scenario, you can use regression methods or clustering or even this or the binning method to infer what this data point is based on the row above it and based on the row below it. So you can fill in noisy data points using that method as well. So as a data pre-processing technique. So this comes as data cleaning. Additionally, you have data transformation, you have data reduction. So in transformation, what you do is you transform it into either lower, you normalize it. Basically, you rescale the values. You drop certain attributes. So you have, let's say, a column that is not really helpful for you in your particular data science perspective. Then you can drop the entire attribute, or you have methods to come up with what attribute is going to be important for your specific scenario that I'll show you. Discretization is basically just removing the decimal points from your floating point data or your decimal data, converting it into integers. It's I would say a bit rarely used because it leads to loss in your data representation, because generally the more information we have in our data set, the better. And concept hierarchy generation is another method of data transformation, but rarely used again. So this was data transformation, and then we have data reduction, where we either have numerosity reduction or dimensionality reduction. We'll touch upon both of these in the coming slides. So yeah, coming to data cleaning, handling missing values in pandas. So as I had mentioned in a previous slide on data preprocessing, so data cleaning, we have the first point as missing data, in which we can either ignore the tuples or fill in the missing values. So and in pandas, we have these four very important functions which help in doing all of these things. So the first function is called the fill NA function. Again, this is I'm copying the code for this function and I'm pasting it in the chat. You can check out each of these functions and their detailed documentation by clicking on the link in the chat. So coming to fill NA, it's basically that whenever there's a missing value, pandas refers to it as NA. These are not NA values which are not applicable or basically missing values. So fill NA is a function which will help you fill these NA values with any predefined value that you might want to fill it with. So it might be 0 or it might be -1, whatever it is that you want to fill it with. Similarly, you have drop NA, which is it just drops the rows which have NA values, or it can drop a column itself with NA values. Then you have interpolate, which is a really good method to fill in or infer missing values based on the rows above and below that particular data point. And finally, we have replace, which can just replace any arbitrary value that you want in the entire data set. It doesn't have to be NA, it can be basically any data point that you want to replace. So in the coming slides, I'm just going to give you small examples of each of these function calls. So we have fill NA. So NA is generally represented as NAN in pandas. And if you take this data frame, so that is what we call as DF, data frame. So A, B, C, D are the column names. 0, 1, 2, 3 are the row numbers. And NAN, as you can see, there are multiple occurrences. If we call df.fill NA 0, so what that means is everywhere that it sees that there is an NAN, it will fill in with 0.0, which is the decimal. Yeah, so the decimal representation of 0. So so this is a very useful scenario, and generally NAN values cannot be pushed into any algorithm, machine learning, or any other numerical computation. So you have to somehow fill in these NA values. You can fill in with 0, or you can fill them in with -1, 1, whatever it is that your needs be. So this is a example of fill NA. Here's an example of drop NA, where wherever there is a row, so in this case, NAN is an NAT. These two are NA values, and wherever there is a row where NA is identified, those rows will be dropped when you call df.dropNA. So the only row that had all the values was row number 1. Row number 0 and 2 had some or the other NA values in any column. So you can customize this drop NA command a lot. I have mentioned the drop NA command ka link in the chat. You can check it out. You can customize that, you can ignore certain columns, you can pick up only certain columns, you can check for only certain kinds of NaN values. So all of that customization is possible, but this is the most basic command that you can give. So coming to interpolate, I think this is an amazing example of interpolate. So zero, so like I said, interpolate is used when you can infer the value of NaN based on the row above it and the row below it. So in this case, we can infer the row above and row below is 1.0, 3.0, and the row in between has been filled in by our interpolate function as 2.0. So this is, I would say, like a really good example of the interpolate function. So, so in all these scenarios, interpolate is very useful, and you can go and experiment with it. Coming to data transformation, in data transformation, we have different methods basically. Excuse me, just a second. Yeah. So in data transformation, we have different methods, which are there are multiple methods, but the most basic one is when we have to rescale values between the range 0 and 1. So here we have min-max scaler, which is part of the sklearn library. So this is a new library that I think brought up. I don't think I've brought it up before, but the sklearn library is extremely useful. It has a lot of these different kinds of transformation techniques, and it even implements a lot of different machine learning algorithms. But for now, let's look at this min-max scaler, which what we do is we very clearly say, please provide a feature range of 0 to 1, and we pass our values which are stored in our data frame. So df stands for data frame. So data frame dot values is x, and we pass this x into our min max scaler, and we say fit the scaler and then transform all of the values. So finally we have the scaled values which we store in another pandas data frame. So so this is a simple example where you have values in the entire data frame, where the values might be in any range from 1 to any arbitrary number, and all of them will be scaled into the 0 to 1 range. So this is called normalization, and it is a very important feature of almost every, I would say it is almost used everywhere, but in machine learning data science, you will see in further sessions, but this is the way to do normalization beforehand. And these are very efficient implementations. You can directly call them, and if you try to code them on your own, they might be less efficient because internally there are many optimizations that are being done within these libraries to make these functions run faster. So I would definitely recommend you using these libraries compared to going for hand-coded normalization techniques. So this is the example of min-max scaler. So coming to second point of our data transformation. So I'll just take you back to the data transformation slide where it says normalization, which we have covered. Next, we'll see attribute selection, and after that, we'll just skip to data reduction. So because these two techniques are rather unused, I would say, not very usually used. So okay, so coming to data transformation, attribute selection is this beautiful technique which gives you a list of attributes ordered in the descending order of importance according to your needs. So let's say that you have a data set where you have multiple columns listed, and finally you have a value that you would like to classify, so your final classification value. So these multiple columns, each of them have a varying amount of correlation with what the final output is. So these three measures, information gain, which can be represented as also called as entropy, Gini index, and gain ratio, these three measures essentially give you very clearly which of the columns in your dataset are most important for your classifier or for your final classification. and you can drop attributes which, if you feel your dimensions are too high, number of columns are too high, you can drop the less important ones and only take the most important columns and use those for your further computation. So this is a very important part of data transformation, and it is regularly used in algorithms like for example, tree-based classifiers, decision trees. These Gini index is commonly used. So also you can use it manually also, but especially when your number of columns or your dimensions are very high. Now moving on to, so I have pasted this link in the chat. You can check out the importance and how to call this function itself. So, or internally how it is, the implementation is. Next, we'll just go to data reduction. So there are data reduction basically means that if you have, let's say, 1 lakh data points, and you would like to represent them using parametric or non-parametric techniques and you would like to represent them in a very condensed format. So let's take a linear example where you have 100,000 data points or 1 lakh data points basically, which correspond to points on a linear scale. So that linear scale can be represented using a line, and the line can be represented using the equation of a line. So this basically means that you have those 100,000 points represented using the equation of a single line. So all you need to have is the equation of the line, which is y equals mx plus c, where m and c are the only two variables that you need to have now. So we have essentially reduced those 100,000 variables or 100,000 data points, sorry, into these two variables which represent the equation of the line, and we can directly infer all of the data points using this equation of the line. So this is a parametric method to represent the entire data set. Similarly, if you have to estimate there are different ways to estimate these parameters. So those are parametric methods for numerosity reduction. You have, like, for example, log linear models, and you have a probability distribution. So you can also represent the entire data set using probability distributions. So it could represent to a normal Gaussian probability distribution, or it could be a modal multi-dimensional probability distribution, but you would have to estimate the probability distribution beforehand, and that is called a parametric method. Non-parametric methods essentially mean storing the data as histograms or clusters, or basically they don't have parameters, they're just a reduced representations of the entire data set. So, or you could just sample a smaller number of data points from the entire data set and consider that as your data set. So that is numerosity reduction. Now, in data reduction, we had numerosity reduction, and the second one was dimensionality reduction. So in dimensionality reduction, the most classic and I would say one of the most useful ones is PCA, which is called as principal component analysis. And internally what it does is it looks at the data using a different approach, and it only looks at it from an axis through which the data has the maximum variance. So that is the simplest way I can put it. But essentially what it does is, if I'm just reading from the slide here, it performs a linear mapping of the data into a lower dimensional space in such a way that the variance of the data in the lower dimensional space is maximized. So you are not having any of the columns retained as is. All of the columns, all of the values will be changed. And if you had 10 columns in the beginning, PCA will give you 2 columns which have maximum variance of the data, but those two are a linear mapping of all of the 10 columns which were originally present. So can be applied using a linear mapping from all of the original columns. So there's a lot of linear algebra that goes behind PCA, calculating the eigenvalues and the eigenvectors and such, but internally it is implemented using scikit-learn, and you can, again, so the link is in the chat, you can check it out. And it is extremely useful when you have too many dimensions and you have to reduce it into a lower dimensional space. Now, coming to handling categorical data. Now, categorical data, as I had mentioned before, there are two kinds of data that you can consider: categorical and continuous. Continuous data is already in the form of numbers, whereas categorical data needs to be converted into categorical encodings. So there is a library called categorical encoding, which is linked here. So a categorical encoding basically means that you have to convert somehow these categories into a numerical representation, which can be ingested by the machine learning or visualization algorithm that you need to use. So there are different ways, many different ways, but here are probably the most useful / most common ones that you would use. So we have ordinal categorical encoders, which basically means that if you take the grades A, B, C, D, E, we will convert A into 0, B into 1, or rather A into 1, B into 2, C into 3, and so on. And that is what it means: convert string labels into integer values 1 through k. This is ordinal. This is used for ordinal variables. Then we have one hot, which basically means that let's say you have 10 categories, then you will the number will have 10 zeros, and only the category which it represents, that column will have 1 instead of a 0. So what it would mean is that basically for one column for each value to compare versus all other values. So this can be used for nominal as well as ordinal. So that means in one hot encoding, you don't need to have any ordering per se. If you don't have any ordering, one hot encoding is the most commonly used encoding, especially to represent, for example, a vocabulary of words in normal NLP task, natural language processing task. A vocabulary of words is represented using one hot encoding because words do not have any such ordering. So we use one hot encoding. So then we have next, we have binary. So where we just convert into an integer using ordinal, and then we convert the integer into binary digits, and each of the digits gets one column. So we use this for the ordinal encoding. Then we have base n. So ordinal here can be considered as base 10 encoding. Additionally, you can also use base n, where the n can be 2, 3, 4, 5, whatever it is. Now this is a very specific use case, not very commonly used, but you can still check it out for your use case. And then finally we have hashing, which is which does incur a bit of loss due to collisions, but ultimately each category will be corresponding to one value that is hashed, that is computed using a hash. So there might be collisions, and collisions means that multiple categories might have the same hash value. So this is another encoding that you can explore. So these are the 5 common ones, I would say. There are many more ways to do it. There are many, I would say, very user specific or data specific ways to do your encoding. But here are the ones that I will leave you with. You can explore further on the link that I posted. So here's an example on how to do categorical encoding. So you import this library called category encoders. Then you call the ce.ordinal encode. This gets you the encoder that you want. In this case, we are using the ordinal encoder, which is this one. And we get the encoder. We get the encoder.fit function, which fits our data into the encoder, which means it converts our whatever data that we have into a format which basically means that it'll fit our data, means it'll look at all of the categories that are present in our data. It'll assign a different ordinal value to each of the unique categories, and finally it'll transform all of the values. So this is the code snippet that you can use to call ordinal encoders. So in category encoders itself, each of these one hot, binary, base n, hashing, and many more are already there. All you have to do is change this ordinal into base n or hashing or whatever it is, and you can call that encoder. These lines of code remain the same for each encoder. So that is a really good feature where you can experiment with different encoders just by changing a single code, single line of code can be changed, and you can experiment with different encoders. So that's very good. So I think that brings us towards the end of this PPT. I think this PPT will definitely be shared with you by Santosh sir, and you can apply all of these techniques on these two very good data sets. And also, you have so many more government data sets. I think you might be aware of it, which can be found at this link here. So please do check those data sets out. You can visualize all the things that you require using these data sets and the techniques that are provided. I'm sure you will be using the pre-processing techniques as well, because there might be missing values. There might be values which you do not want to pick up. So you will have to pre-process it. You will have to encode them using category encoders. Then you will have to visualize them using any one of the specific visualization techniques that we use. So, and then we have then I have just provided a small list of really interesting visualization applications. You can go through them. And finally, at the very end of the slides, I have provided a small cheat sheet for you where you can very easily figure out what kind of data representation technique you should use for different scenarios. And this is a very application specific, it's not technical at all. So very application specific cheat sheet. And yeah, so please do go through this when you get the slides. Yeah, so I think that is pretty much it. We have a final further reading section at the very end. I think this is the last slide, and thank you very much for attending this session. If you have any doubts, we can have them right now.
You're allowed to unmute yourself. If you have any sort of questions, you can ask. If there are no specific questions, we
Good
shall have a
afternoon,
brief.
sir. Good morning, sir. Sir, I want to ask one question about one hot encoding. Uh, According to that, if we have a 10 column, then that will be converted according to that, no? One versus compared to all other columns. So if we have 1000 column, then isn't it will increase the dimensions of the data?
Yes, ma'am. Sorry, just a second. I'll just clarify what one hot encoding does. So I think I'll explain it using the chat section itself. So let's take. So one hot encoding is applied to, or any of the encoding techniques are applied to each specific column. So let's say you have one column which represents gender, for example, and let's assume that you have two genders right now, male and female, right?
Okay.
So we have two genders, male and female. So in this case, the one hot encoding for male will be represented as 01, and the one hot for female would be represented as 10. So this is what one hot encoding means. So did that make sense? So how this is represented, and now the columns, that this gender column is split into two columns, where the first column represents the first digit and the second column represents the second digit.
Yes, sir.
Right? So let's say you have 10 categories in your column. So you have 10 categories A, B, C, D, E, up to 10 alphabets. So those 10 categories, if you have to represent category A, then A will be represented as 1 followed by 9 zeros, like this. So and B will be represented as 0, 1 followed by 8 zeros.
Okay, sir.
Yeah, I hope that makes sense. One second.
Okay, sir. Thank you.
Okay, sir, I need to ask one question.
Yeah.
you had shared one link that was regarding the data that we can use for the purpose of pre-processing. I had visited this site once, but I found that month-wise there is no proper data available, and again the fields that are mentioned in the mostly they are CSV files. There is no explanation for the fields as well. So do you have other sites where we can go for the data where we know, like, okay, these are the fields and the explanation of the fields are also given? Because there are short names of column given and few are not at all understood, like for what purpose these fields are for.
Okay, fine. So can you mention the site which you had referred to, which you are referring to here?
Yeah, the one that you mentioned, that is the government site, and I was looking for road accidents.
Oh, okay. Oh, you're talking about the government data. Okay.
Yes.
So yeah,
So
there
yeah,
is
the site that you mentioned, I had visited it for the sake of getting some data, but I didn't find it relevant, because I didn't find having most of the yearly data, as well as the file had only few
yes.
fields, and the fields had no explanation like what these fields are for.
Got it.
So if possible, can you also share some
Sure.
links where we can find more better presentative data where we can work on?
Yes, of course. So
Okay, thank you.
I have two examples for that.
Okay.
One is Kaggle.com and the
Yes.
other is Google itself provides
Okay.
a dataset search utility. So the link for that I have provided in the chat.
Okay.
It will search only for datasets, and you can search for any dataset in this link. So
Okay.
yeah, so these two. So if you're specifically looking for road accident dataset, then
Okay.
refer to the Google one, because they provide from, like, Google has an extremely good search engine, so they know which datasets are there in every corner of the internet, right? So I would definitely recommend that dataset search.research.google.com.
Okay. Thank you so much. Okay.
Yeah.
And we can have one more doubt if any. And further, if participants have any other doubts, they can keep them in the group so that it will be answered. So if there are no further doubts, we shall break for 10 minutes and further session will start after 10 minutes of break. And Vedant, thank you so much for your presentation.
Yeah, thank you so much for listening, and hope you gained some good information from this. Yeah, thank you, sir.
Thank you.
Yeah, thank you very much, sir.
So we shall break for 10 minutes and then the next session will start.